Myself N. Rashima, Assistant Professor of Mathematics, Haji Kattaraktar Navdiya College, Vikamapalayam. Let us discuss about relations in discrete mathematics. Now let us start with a definition of Cartesian product of sets. The Cartesian product of the set A and B can be written as A cross B, which is a set of all ordered pair. In this ordered pair, the first element are in A and the second element are in B. That is A cross B equal to set of all x comma y. Here x belongs to A and y belongs to B. For example, consider A equal to 1 comma 2, B equal to A, B, C equal to alpha, beta. The Cartesian product of A and B can be written as every element of A is paired with each element of B. That is 1A, 1B, 1C, 2A, 2B, 2C. Similarly, A cross C can be written as 1 alpha, 1 beta, 2 alpha, 2 beta. Next, from the definition itself, we can know that A cross B is not equal to B cross A, and the relation A comma B comma C belongs to A cross B cross C. This is triple ordered pair. Here A comma B belongs to A cross B and the element C belongs to capital C. Likewise, A cross of B cross C can be represented in the same way. Also that A cross B cross C is not equal to A cross B cross of C. From this result, we can say that Cartesian product is not associative. Now, A cross A is represented as A square. The element of A is paired with element of A. X comma y for all xy belongs to A. Also, we can form A power n equal to A n minus 1 cross A. One more important note is that if A has n elements and B has m elements, then A cross B has m n elements. The problem related to Cartesian product, if A equal to 1 to 3 and B equal to A, B, then we can find this Cartesian products, that is A cross B cross A cross A and A square cross B. As we noticed in the example itself, A cross B can be written as every element of A is paired with each element of B. That is 1A, 1B, 1A, 1B, 2A, 2B, 3A, 3B. If B cross A, B should be the first element. That is A1, A2, A3, B1, B2, B3. A square, in A square, A is related to A. So 1, comma 1, 1, comma 2, 1, comma 3, 2, comma 1, 2, comma 2, 2, comma 3, 3, comma 1, 3, comma 2, 3, comma 3. In this way, we have to relate it. Next, A square cross B. First, we need to find A square, then we are producting it with B. Next problem is A cross B intersection C is equal to A cross B intersection A cross C. First, we are considering one element in B intersection C, that is x comma y belongs to B intersection C. This can be written as x belongs to A and y belongs to B intersection C. We can split this relation as x belongs to A and y belongs to both B and C. Again, we are splitting the terms. We get the relation as x comma y belongs to A cross B, x comma y belongs to A cross C. Both the relation is combined as x comma y belongs to A cross B intersection A cross C. This shows that A cross B intersection C is contained in A cross B intersection A cross C. Similarly, we can do the converse part. This problem is also similar to problem number 2. Next, introduction to relation. Any subset of A cross B is called a relation between A and B. Also, any subset of A cross B is called a relation on A. So first we need to form the Cartesian product, and forming the subset will be the relation. If A is a relation, any set of ordered pair with a component in A is a relation on A. If R is a relation on A, the element in R is as x comma y belongs to R, written as x R y. That is, x is related to y. If x is related to y, we can return as x comma y belongs to R. If they are not in relation, x comma y does not belongs to R. Here are some examples. If x comma y belongs to F, then X is a father of Y. This is one relation. Next, L in L, X comma Y are related as X and Y are real number and X should be less than Y. These two are examples of relation. Next example is A comma B be any two sets, then any non-empty subset R of A cross B is called a binary relation. Here, consider A equal to 1 to 3 and B equal to A comma B. Then the Cartesian product can be written as 1A, 2A, 3A, 1B, 2B and 3B. From this Cartesian product, we can able to construct a relation that is subset of this Cartesian product R1, R2, R3, subset of A cross B, which is considered as a relation. Next concept is domain and the range of a relation. Let S be any binary relation. The domain of S is a set of all element X such that for some Y, that is, when X comma Y belongs to S, this number of X is a domain denoted as D of S equal to X such that X comma Y belongs to S for some Y. Next, the range of S is a set of all element of Y such that for some X, that is R of S equal to Y, where X comma Y belongs to S for some X. The example for domain and the range is if S equal to 1A, 1B, 2B, 3A. Here 1, 2, 3 are the domain and the range is A and B. When x is equal to y, x cross x is called the universal relation. When x is empty, it is called void relation. Next, operation on two relations. Here, considering two relations R and S, R union S consists of elements such as x comma y. X is related to y in either R or S. And x intersection S is x comma y. Here, x and y are related both in R and S. Next, R minus S. Here, x comma y are related in R but not in S. Also, R plus S is x and y is related either in R or S but not both. Next important property in relation is, first one is reflexive property. Let R be a binary relation defined on X. R is reflexive only when the element X is related to the same element X in R. For example, here X is a set consist of 1, 2, 3 and the relation R is defined as 1, 1, 1, 2, 2, 2, 3, 3, 2, 3. And same, the relation S is defined as 1, 1, 1, 2, 2, 1, 3, 3. Here R is reflexive because it consists of 1, 1, 2, 2, 3, 3. But S is not reflexive because it does not consist of 2, 2 in the set S. Next is symmetric property. A relation R from X to Y is symmetry whenever x comma y belongs to R, then y comma x should belongs to R. That is x r y implies y r x. Then R is symmetric. Example is here we are considering the same example. R is symmetric but S is not symmetric. This is because here 1 comma 2 belongs to S, but the inverse element of 1 comma 2, that is 2 comma 1, does not belongs to S. Next, transitive property. A relation R is transitive if x comma y belongs to R and y comma z belongs to R. Combining these two relations as x comma z belongs to R. If x r y and y r z implies x r z, then z is transitive. Here is one example. Considering the two relations R and S, R is transitive but S is not transitive. This is because 2 comma 1 belongs to S and 1 comma 2 belongs to S, but the element 2 comma 2 does not exist in the same set. Next one is irreflexive. Irreflexive is complement to reflexive property. A relation R in a set X is irreflexive for every X belongs to X such that X comma X does not belongs to R. Example for this irreflexive is same, considering the two relation R and S. Here R is irreflexive but S is not irreflexive because 3 comma 3 does not belongs to S. Next one is antisymmetric. A relation R in a set X is antisymmetric if whenever x comma y belongs to R and y comma z belongs to R, then x should be equal to y. If R, x, R, y and y, R, x implies that x equal to y. Next one is a relation matrix. Let x equal to x1 to xm and y equal to y1 to ym are the ordered set. A relation R is defined from X to Y, then the matrix relation is defined as MR equal to Rij. I varies from 1 to M, J varies from 1 to N. Example for is we can construct the matrix using this relation. Here 1 comma A, 1 is paired with A, 1 is related with B, 2A, 3B. So we have to, in the matrix, we have to put 1 if they are related, and if they are not related, we have to put 0. Next one is composition of binary relation. We have let R be a relation from X to Y and S be a relation from Y to Z. We need to composite this both relation as R composite S, which is defined as with the example that R and the S are the relation. R composite S can be related using the transitive property. Here 1 comma 2 in R, 2 comma 1 in S is related as 1 comma 1 in the composite function. And 1 comma 2, 2 comma 3 implies 1 comma 3. The composite can be done by using the transitive property. Next, composition in matrix format. The two matrix can be composited by MR composite MS equal to MIJ. Here, whenever MIJ is equal to 1, if and only if the ith row and the ith row of MR and jth column of MS has 1. We can form the relation into matrix and we can compose it by comparing the ith row of MR and jth column of MS. Next one is equivalence relation. The equivalence relation is that if the relation satisfies the three properties, that is reflexive, symmetry and transitive, then the relation is an equivalence relation. Here some examples. X is a set consists of 1, 2, 3, 4 and R is a relation. You can check the reflexive, symmetry and transitive property on this relation R. Also that equality of subset on a universal set is an equivalence relation. Next example is X consists of 1, 2, 3, 4 up to 7. R is a relation such that X comma Y is divisible by 3. In reflexive property, x minus x equal to 0, which is divisible by 3, hence R is reflexive. Also, in symmetric property, we can say that when x minus y is divisible by 3, then y minus x is also divisible by 3. And in transitive property, we can state that x minus y is divisible by 3, y minus z is divisible by 3. Then summing this two relation, we get x minus z. It can also be divided by 3. Therefore, it satisfies the 3 property. The relation R is an equivalence relation. Thank you.